Okay, so we'll take a look at another electromagnetics question. Here we are told a horizontal wire with mass per unit length of 0.05 kilograms per meter carries a current of 5 amps to the left. We are asked what is the minimum magnetic field needed to lift the wire upwards. Okay, so we're going to think about the force. We know that force is equal to the length of the wire times the current it carries times the strength due to the magnetic field. Now we are told the mass per unit length is 0.05 kilograms per meter. So this tells us that in 1 meter there's 0.05 kilograms. So let's think about 1 meter of this stuff. We don't actually have a force number in our formula. We have a current, which is 5. The magnetic field is what we're going to be finding. L, we're going to arbitrarily choose to be 1, but we don't have a force. Well, the force is going to be gravity. So if we take 1 meter as our base case, the force due to gravity is mass times gravity, and this is going to be downwards, which means the field direction will need to be such that the magnetic field force is upwards. But we just care about the magnitudes, not the directions. So this is going to be 0.05 multiplied by about 9.8. So 0.05 times 9.8 gives me 4.9 times 10 to the minus 1. 4.9 times 10 to the minus 1, and this is newtons. So this is going to be the magnitude of the force. So we need to solve for the field strength B. So divide both sides by I and L. This tells us that B, the field, is the force divided by the length multiplied by the current. Well, the force required from the field has to be equal in magnitude to the force due to gravitation, in the opposite direction of course, but equal magnitude. So 4.9 times 10 to the minus 1. This is divided by the length of the cable. Well, we took this to be 1 meter, so this is going to be 1. And then we're going to multiply this by the current, which is 5 amps. So if we put this in our calculator, this is going to decimally approximate this number for us. So we'll get 4.9 times 10 to the minus 1 divided by 5. My calculator tells me that is 9.8 times 10 to the minus 2. 9.8 times 10 to the minus 2. And that should be in Teslas. So this is the strength of the magnetic field required to keep the object from falling. A field any weaker would allow gravity to overcome the force due to the magnetic field and the object would fall, accelerate downwards. A force stronger would lift the object upwards. And if we draw a little diagram of this, we can sort of see which direction the field has to go, depending on which way the current goes and all of this. We know that gravity definitely is pulling this thing down. Let's say that our current goes this way. So I goes to the right. We use our right hand rule. In order for the force to go up, current goes to the right, our field has to go into the page. So we have to have a field that goes into the page like so. The magnitude of that field has to be 9.8 times 10 to the minus 2 Teslas. This will generate a force on this object upwards that is equal to the gravitational force. So this is force due to gravity, this is force due to the field. If the field has this strength, these will cancel each other out and the wire will just levitate. So this field strength makes them levitate. We've got to be very careful. The question asked us, what is the minimum magnetic field needed to lift the wire upwards? It's technically B greater than 9.8 times 10 to the minus 2 Teslas. You would need the value to actually be slightly larger than this to lift the object up. If it was exactly equal to it, the object would just levitate. It would not actually lift up, because we're told in the question lift the wire upwards. So a field greater than 9.8 times 10 to the minus 2 Teslas. So this is the answer that we're after for this question.